In this video, we solve problem 14.7.019 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use cylindrical coordinates to find the volume of the solid, and we're told that the solid is bounded by r squared plus z squared equals 49, that's a sphere, and the cylinder r equals 7 times cosine of theta. So just as a quick reminder, or a quick derivation actually, this is a circle and it's not centered at the origin. It's centered either on the x-axis or y-axis. So if you want to figure out which one that is, you just take that equation, r equals 7 cosine of theta, and you multiply both sides by r. And that's going to give you the r squared that you need and the r cosine of theta that you need in order to convert this easily to rectangular coordinates. So after multiplying both sides by r, we know that r squared is x squared plus y squared, and r cosine of theta is actually equal to x. So we have that. Now if we subtract 7x from both sides, this is what we get. And then we would typically complete the square here. So we would add half of negative 7 divided by, or half of negative 7, which is negative 7 divided by 2, squared to both sides. So it's going to give us a 49 over 4 that gets added to both sides. So this is actually x minus 7 over 2 squared plus y squared equals 49 over 4. So that means we have a circle of radius 7 over 2, which is 3.5. Centered at x equals 3.5, y equals 0. So in the xy plane, what we would see is this. I'll just put that 3.5 right there. I'll try to keep it to scale, but I'm not going to add all the extra tick marks. Not bad. It's close to a circle, but not quite. So that's approximately our circle, and it's given by r equals 7 cosine of theta. And this is a sphere, which we can see pretty easily if we take r squared and replace it by x squared plus y squared. That is a sphere centered at the origin with radius 7. So that's going to look like this, roughly. Oops, it's very rough. So basically we've got a cylinder that is taking out a piece of this sphere. That cylinder is centered at 3.5, x equals 3.5, y equals 0. And then it is sort of intersecting this sphere at the bottom and in the top layer. So there's just a part of a sphere that's cut out by a cylinder that looks like this. So the cylinder actually looks like that. And it is sort of up against the z-axis like that. These aren't great pictures, but I hope you get the idea. Well, we're asked to find cylindrical coordinates to find the volume of the solid. So you've got basically this as your formula. You want the triple integral of v times dv. That's what you want your volume to be. Or I guess I should call the solid region Q. And the solid region Q that we're talking about is the part of the sphere that is inside this cylinder. So we're going to have a little part of the sphere at the top, a little part of the sphere at the bottom, and a cylinder inside that. Well, that is the triple integral over Q of, in cylindrical coordinates, you can use r times dz, dr, d theta. And then we can use this equation to get the bounds for z. So r squared plus z squared equals 49. And if we solve for z, we get z squared equals 49 minus r squared. And then if we want to get c by itself, we take the square root. So we have plus or minus the square root of 49 minus r squared. The positive square root is the top part of the circle, or excuse me, the top half of the sphere. And then the bottom, or the negative square root is the bottom half of the sphere. This picture is really horrible. I'm sorry. It doesn't look like it's even going through those points where they're supposed to go through. That's okay. It's just a cartoon. It's just to give us the idea of what's going on. Okay, so we've got our bounds for z. And then the bounds for r come from the region in the xy plane. So r starts at 0 and it goes out to this curve. So r is between 0 and 7 cosine of theta. And you can use lots of different bounds for theta. I prefer to use the bounds that get me from the negative y-axis to the positive y-axis. So I would say that I'm just thinking of angle, theta being an angle that sweeps from down here to up here. So theta goes from negative pi over 2 to pi over 2. So our bounds are this. We have the integral from negative pi over 2 to pi over 2 of the integral from 0 to 7 cosine of theta of the integral from negative square root of 49 minus r squared to the positive square root of 49 minus r squared. And we are integrating with respect to z first, then r, and then theta. The antiderivative of z, or r with respect to z, is just r times z. And we evaluate from this lower bound to this upper bound. And that leaves us here. I can factor out the r, and then I'll have this positive square root minus the negative square root. Subtracting a negative is adding. So we're going to end up with 2 times the square root of 49 minus r squared. Then we anti-differentiate with respect to r. I would use a u substitution. 49 minus r squared is our u. Du is negative 2 dr. Multiply both sides by negative 1 to get that 2r dr by itself. And then we need new bounds. So u is a function of r. We're replacing r with 7 cosine of theta. So we end up with 49 minus 49 cosine squared theta, which is the same as 49 times 1 minus cosine squared theta. And we know from our Pythagorean identities that cosine squared plus sine squared is 1. This is actually cosine squared plus sine squared minus cosine squared. So it's just going to give us a sine squared as our upper bound. And if r equals 0, we get this, just 49. So that's our new lower bound. Okay, so we have this integral. I'm going to move over to the side here because I have plenty of space and I've sort of I've limited myself by working over here. This becomes the square root of u, or u to the 1/2, times 2r dr, which is negative 1 du. And that's our integrand. And then we're taking the integral of that expression from u equals 49 to u equals 49 sine squared theta. And we're still working on the inside and working our way out. Oops, thought that was a blue marker. Or blue Sharpie, I should say. So we add 1 to the exponent. It's going to give us 3/2, and then we divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And then we evaluate this from u equals 49 to u equals 49 sine squared theta. And we want to be careful about this. We need to think about what we'll get when we take the square root of this and then cube it if we're on the interval from -π/2 to π/2. That would require looking at our sine function. So the sine function looks like this, right? It repeats every 2 pi. And if I go back pi radians, it looks like this. So when I use these bounds from -π/2 to π/2, sine is positive on the interval from 0 to π/2 and negative on the interval from -π/2 to 0. So I want to keep that in mind when I substitute and simplify. I'll factor out, oops, that's a -2/3, the -2/3. And we have the integral from -π/2 to π/2 of the this expression raised to the 3/2 power. So we'll have 49 sine squared theta raised to the 3/2 power minus 49 raised to the 3/2 power. And 49 is a perfect square. So if you want, you could take this 49 to the 3/2 and you could write it as the square root of 49 cubed. That's probably, well, that's exactly, excuse me, what I would do. So we just get 7 cubed, and I actually don't know what 7 cubed is. That turns out to be 343. So we're going to have a factor of 343 here and here. I think I'll factor that out from everything. And actually, let's factor out a -1 times 343. So we'll have 343, or -343 times -2/3 is going to give us positive 686, all divided by 3. And flipping that in that way changed the order. So instead of having this minus this, because I factored out the -1, I'm going to have this minus this, but we factored out the 49 to the 3/2. So what we end up with is 1 minus sine of, or the sine squared theta raised to the 3/2 power. Now on the surface, you might think that's sine cubed. And that's exactly what we would get if this sine function was always positive on the interval from -π/2 to π/2. But it actually has different signs on the interval from -π/2 to π/2. So that's SIGN signs. Let's think that through. So we've got this 684/3 out here. And then we have the integral from -π/2 to π/2 of 1 minus sine squared theta raised to the 3/2 power, which you can think of as a sine squared theta raised to the 1/2, all cubed. The reason why we're thinking of it that way is because this is going to have a different value depending on what interval we're on. So if we're on the interval from -π/2 to π/2, so we're on this interval here. Sine is positive on this interval and it's negative on this interval. The way we need to handle this or treat this is that we get 2 different values for the square root of sine squared on the interval from -π/2 to π/2. If we're taking the square root of x squared, just in general, that's going to give us x back as long as x is greater than or equal to 0. But if x is negative, let's say you plugged in -2 here, -2 times -2 would be +4, and you take the square root of +4 and you get +2. So the output of this is always positive, even when x is negative. So what we get when we plug in a negative value here is actually -x. And if you're saying that's not supposed to be a negative number, it's not a negative number. It's a negative number times a negative number, which makes it a positive number when x is negative. So in the same way, when, oh, actually we're taking sine, oh no, just kidding. In the same way, when I have a sine of theta playing the role of x, I'm going to get sine of theta when sine of theta is greater than or equal to 0, which we can see happens on the interval from 0 to pi/2. And I'll get negative sine of theta, which is a negative times a negative, which makes it positive on the interval where sine of theta is negative, which is on this interval here. So when we take this expression and we raise it to the third power, we take this, which is this, and then we cube it. That's what we get. We have to be very careful about these SIGN signs because they lead to different results. So what we're going to have is this integral from, or this 684/3 times the integral from -pi/2 to 0 of 1, and then we want 1 minus this expression. Well, on the interval from -pi/2 to 0, this expression is that expression. So it's going to be a negative sine of theta cubed, and we're subtracting that. So that means we're actually adding a negative times a negative equals a positive sine cubed theta. And then we're going to add the integral from of 600, I think I wrote a 4 there, and it should be a 6. 686/3 times the integral from 0 to pi/2 of this expression here. And sine cubed theta is the same as sine squared theta times sine of theta. And I would use that and our Pythagorean identities and our trigonometric integrals methods in order to evaluate that expression. So sine squared is actually 1 minus cosine squared. So I would use a u substitution for this, where u is equal to cosine of theta. I would use that for this integral and this integral. Whoops. On this one, sorry. This is positive sine cubed theta, and we're subtracting it. So there should be a minus sign there. Okay, so let me write all of this out sort of longer with the 686/3 factored out. I have the integral from -pi/2 to 0 of 1 plus the quantity 1 minus cosine squared theta times sine of theta d theta. And then I have the integral from 0 to pi/2 of 1 plus, or excuse me, 1 minus cosine squared theta times sine of theta d theta. Let's do the easy part first. The antiderivative of 1 with respect to theta is just theta, and then we're going to evaluate that from -pi/2 to 0. And then the rest of this, we need a u substitution. So I'll just write it in as an integral for right now, and we'll do the u sub for this. Similarly, take the antiderivative of 1 over here. We just get theta. We evaluate from 0 to pi/2. And then we're subtracting the integral from 0 to pi/2 of 1 minus cosine squared theta times sine of theta with respect to theta. Okay, so we'll let u equal cosine of theta. Then du is negative sine of theta d theta. And then we'll multiply both sides by -1. So this is -1 times du, and this is 1 minus u squared. I'm sorry, I'm seeing that there are sign issues. No, actually it's fine. That's a plus and that's a minus. Good. And this is actually going to be identical to that. We're using the same u substitution. We're just going to have different bounds for these guys. So we'll have 1 minus u squared here, and this is a -1 times du. And then for the bounds, we evaluate cosine of theta at 0 and -pi/2 for this integral. And then for this one, we evaluate cosine of theta at pi/2 and 0. At 0, we just get 1. And at -pi/2, cosine of -pi/2 is the x value on the negative y-axis. So it's going to be 0. And at +pi/2, we get 0. Okay, so those are our values. I was thinking through the unit circle there. That's what that was about. Sorry about that. Okay, so now we have these expressions. So we have 686/3 times 0 minus a -pi/2. So that's 0 plus pi/2 plus 686/3 times this integral. So we'll have the integral of 1 minus u squared times -1. So you could call that u squared minus 1 if you want to. And your bounds are 1 and 0. Over here, oops, there's a 686/6 multiplying this guy as well. So you have pi/2 minus 0 there, which is just pi/2 minus the value of this integral. I have a negative du times this. So the negative times the negative would make that a positive. And then we have an integrand of 1 minus u squared du, evaluated from the lower bound of 1 to the upper bound of 0. Okay, now we can actually flip these if we multiply by -1. So we end up with 686/3 times pi/2 here, plus another one of those. So I've got 2 of those. That's taking care of this guy and this guy. And then I have 686/3 times this integral. And then I can flip these bounds if I multiply by -1. But multiplying this by -1 is just the same as changing that into a u squared minus 1 there. So I actually have 2 copies of the same integral. So we have 686 times pi/3 over here. And then we have 686/3 times 2 of these integrals. And this I would evaluate by adding 1 to the exponent and dividing by the new exponent. The antiderivative of 1 with respect to u is just u, and then you evaluate from 0 to 1 there. And I'm leaving the 686/3 factored out because I think I'm going to factor it out from the whole thing in just a moment. So we'll have 686/3 times pi is this first term, plus 2 times whatever we get over here. This is 1/3 minus 1. 1/3 minus 3/3 is -2/3. And then when we evaluate this at u equals 0, we get 0. So we just have -2/3 minus 0, which is 0. And so that ends up giving us 686/3 times pi minus 4/3. If you want, I guess you could factor out a 1/3 as well. So you could go to 686/9 times 3 pi minus 4. And that's probably how I would leave my answer.